All right, so um, today we're going to talk about proofs and a strategy that the book in section 7.1 talks about a lot called the indirect proof strategy or the reductio ad absurdum strategy. Yeah, so that's what we'll be covering. So here is a propositional proof in English rather than logic. From statements 1 through 4, we are going to talk about how to prove statement 5. So the 4 statements are: the only people in the mansion were the butler and the maid. If the only people in the mansion were the butler and the maid, then either the butler or the maid did it. If the maid did it, then she had a motive, but the maid didn't have a motive. From statements 1 through 4, we are going to try to prove statement 5 that the butler did it. So what we're going to use, as I said before, is called the indirect proof strategy, which works something like this. I'll give you a minute to finish jotting this down. I see a couple of you. So the goal is from statements 1 through 4, we want to prove statement 5. Now, last time I showed you some sort of straightforward strategies using S and I rules. And you could use those strategies without the indirect proof strategy to prove this. But we will look at some things today that you would need this new strategy in order to prove. So again, this is called the indirect proof strategy. Here's how it works. You start with the given assumptions from the problem, and then you add a separate assumption that you intend to disprove or refute. The way you're going to disprove or refute that added statement is you are going to show that it leads to what is called a logical absurdity or a logical contradiction. And a logical absurdity or a logical contradiction is something very specific. It is when you have the same claim being both true and false at the same time in the same way. So if when we add a new assumption, if adding that new assumption leads to a situation where a certain proposition is both true or false at the same time, it shows that that assumption is incorrect and is disproven. And by the way, the contradiction doesn't have to be a simple thing. It can be something more complex like this. So this is also a logical contradiction. So this says both A and B are true. This says it's not the case that both A and B are true. That is equally as much of a contradiction. All right, so step 1, you add an additional assumption which is meant to be refuted. The standard thing to do that Gensler is going to teach us to do is to start by assuming the opposite of the intended conclusion. Once you make the assumption you wish to disprove to derive the opposite of, you then use the S and I rules along with that new assumption to demonstrate that adding that new assumption leads to a direct logical contradiction where some claim or some complex claim is both true and false at the same time. When you have accomplished that, then step 3 is you may conclude the opposite, you may infer the opposite of the original assumption as true. The indirect proof has demonstrated that the opposite of the initial assumption is true, is the case. All right, so let's use this with the butler and the maid story. So the only people in the mansion were the butler and the maid. If the only people in the mansion were the butler and the maid, then either the butler or the maid did it. If the maid did it, then she had a motive. But the maid did not have a motive. All right, so what does this look like using the indirect proof strategy? It looks something like this. We start by adding the additional assumption, the opposite of what we intend to prove. We want to add a fifth claim that the butler did not do it. Once we've added that, we start using our S&I rules. And this is the first time, I think, in this class we've been trying to use S&I rules with English rather than logic, but it shouldn't be that hard to track what we're doing here. If you look at statement 1 and statement 2 is an arrow conditional statement, an if-then statement. Says if the only people in the mansion were the butler and the maid, then the butler or the maid did it. So the left half of the arrow statement is found in statement 1, that the only people in the mansion were the butler and the maid. So from the combination of 1 and 2, you can infer out the second half of statement 2. You can infer out that either the butler or the maid did it. From statements 1 and 2, from the modus ponens left to right arrow rule. And once you have 6, you can use 5 along with 6. 6 is an or statement, the butler did it or the maid did it. And 5 denies half of the or statement. 6 says either the butler did it or the maid did it, but 5 says the butler didn't do it. So when you have an or statement and the negation of one of the halves, you may infer out the remaining half. So from 5 and 6, you should infer that the maid, in fact, did it. Then once you've got 7, that the maid did it, you may plug that in with 3. 3 is another arrow conditional if-then statement. If the maid did it, then she had a motive. And 7 says that the maid did, in fact, do it, plugging in the left side of the if-then statement. We may infer out 8 that the maid, in fact, did have a motive. But once we've got that, then we have a problem. The problem is this. 4 says the maid does not have a motive. 8 says the maid, in fact, has a motive. That is a direct logical contradiction. It is an absurdity. Both those claims can't be true. What is the problem? The problem is statement 5. Statement 5 leads to a logical absurdity that can't possibly be the case. Statement 5 leads to the maid both having and not having a motive. Because statement 5 leads to the maid both having and not having a motive, a logical absurdity, we may infer out the opposite of what we claimed in 5, that the butler must have, in fact, done it. And that was what we were to prove. We are done. Mission successful. Questions, thoughts? Does this make sense? Yes, sir.
So when we're getting the final conclusion from all the premises that we're assuming, we're making sure that it's the opposite of what we want to conclude.
So remember, we decide what we want to prove, and then we add the assumption, which is the opposite of what we want to prove, because we want to show that the opposite leads to stupidity, leads to absurdity. And that's what we did here. The goal was to prove the butler did it, so we did this hypothetical. Well, what would it look like if the butler didn't do it? And then we say, well, gee, the maid has no reason to do this, so the butler must have done it, not the maid. Very good, young Ravenclaw. All right, we're going to talk about this a couple different ways. So now let's look at it by providing the logical translation. So again, the translation back and forth is helpful, and sometimes some people follow the logic better, some people follow the English better. So if I want to translate this proof, it would look something like this. The only people in the mansion were the butler and the maid. T. T for the only people. If the only people in the mansion were the butler and the maid, then the butler or the maid did it. If T, then B or M. If the maid did it, then she had a motive. If M, then H. But the maid didn't have a motive, not H. From this, we're going to try to prove that the butler did it. B. And now we're going to drop off the English and just show you the logic. So without English, just in logic, it would look something like this. T, if T, then B or M. If M, then H, but not H. From that, we will seek to prove B. First thing we do, we assume the opposite of the intended conclusion, so that we will show that the opposite of the intended conclusion leads to absurdities. So we'll start by proving not B. That's step one. All right, so after we've got our not B, then we will look at our given claims to derive more things. So if you look at 1 and 2, 1 says T, and 2 says if T, then B or M. So our inference in statement 6 will be that B or M must be the case, because we have T, and we have if T, then either B or M. That is from statement 1 or 2, 1 and 2, with the arrow rule going left to right called modus ponens. All right, what do we do next? Well, then, from B or M, which is an or statement, and not B, we can infer M, because 6 is an or, and 5 denies half of the or. So we are left with M from 5 and 6. Then we take 7, which is M, and we look back at our given premises, and 3 says if M, then H. So we get H from the combination of M and if M, then H. But then we have a problem. We have H in statement 8, but we had not H in statement 4. H is true and H is false in the same time, if we assume the butler did it. Therefore, from statement 5 and the fact that it leads to a contradiction between 4 and 8, we may infer the opposite of statement 5. We may assert B. So that is what the indirect proof looks like in logic. Yes?
So in like simpler terms, just like disproving the opposite of the job in order for
So you think this is simpler? I'm sorry, so what was your question?
so like, is it just trying to disprove the opposite of, all right,
So yeah, so the goal here is to take the opposite of what the goal is to prove and show that the opposite leads to absurdities, leads to things that can't be the case. All right. And if you do that, then you win and you get to infer out what you intend. Now, Gensler really likes this strategy. In fact, he doesn't even teach you that it's possible to do a proof without this strategy. Which is why we had our lecture on Friday, where I showed you how to do multiple step proofs without doing this, because I think going straight to this is a little more complicated than what we were doing last Friday. But this is also more powerful than what we were doing last Friday. And there are things you can prove with this that you can't prove from just using the S alone, which is why Gensler likes this strategy. All right. So let's pause in our discussion of proofs. And now I'm going to throw an extra S rule or extra couple of S rules your way. Now, I don't think anything we do will use double negation, But just in case it comes up, or in case you were wondering, if you are ever inclined or ever in a position where you can negate negation, a double negation is the exact same thing as an affirmation. So it's like multiplying two negative numbers or using a double negative in English grammar. They cancel each other out. So if I say that I think it is not the case that the defendant is not guilty, well, not guilty means I think he's guilty. The nots cancel each other out. The negations cancel each other out. That's not good English grammar, but in logic, you can say all sorts of things. I don't think that will come up, but just in case it does, you've been told. These other two things, however, will definitely come up. So I taught you S&I rules for every one of the operators except triple bar. So here are the rules for triple bar and negated triple bar. Triple bar, P triple bar Q implies if P then Q and if Q then P. Or, as I like to say it, both sides will always match. That is the claim. In fact, some logic systems don't even use a triple bar. They like to use a double-sided arrow. So when I see something like if A triple bar B, what I actually see is something like this. A double-sided arrow B, which means if A then B, and also if B then A. Now, I think that's the easier of the two. The one that people get wrong most often is this next one, so I strongly encourage you to memorize this one. Negated triple bar. Negated triple bar means either, negated P triple bar Q implies either P or Q, but not both P and Q. Or to say it differently, negated triple bar means one side is true and one side is false. They can't both be true and they can't both be false. One has to be true, one has to be false. So P or Q means one of these two is true, P is true or Q is true, but not both P and Q means one of the two sides has to be false. So add that to your repertoire of S rules and I rules and be ready to use it on the exam and in the exercises as we proceed. All right, let me show you something that I think is kind of cool. And this is the sort of thing, this is the sort of reason that Gensler really likes the indirect proof, the RAA, reductio ad absurdum style proof. This is a proof with no given premises. So what this is intended to prove is that if both A and B are true, then A must be true. But we're going to give you no premises to work with. How can you prove this? Well, you can use the strategy that we've been talking about. Step one, take the opposite of the conclusion. So we have negated if both A and B, then A. That's the first step. Now, once we have negated if both A and B, then A, then we can use our rule for negated conditional, for negated arrow. And that rule, negated if then or NIF, allows us to infer out the exact match of the left side of the arrow of both A and B, and the exact opposite of the right side of the arrow. So A becomes negated A. Then we can look at 2, and from 2 we can infer A is true and B is true, but we don't really need to use the B, so we'll just infer out A is true from 2, half of the AND rule. And as soon as we do that, then we have a logical absurdity, because both 3 and 4 contradict each other. 3 says A is false, 4 says A is true, and if, denying that if both A and B, then A, if that leads to A being true and false at the same time, then we may infer out the opposite of our initial assumption, because 3 and 4 contradict. All right, let me get a sense of the class. How are we doing? Give me 2 thumbs up if you got this. Give me a wavering thumb if you're not sure, and give me a thumbs down if you're lost. All right. So some of us are wavering a little bit. What point are we wavering at? What's unclear? What can I help you with? Yes.
I think it's mainly just seeing how the rules apply, since if the idea is we're working backwards, it's just trying to figure out how the rules apply exactly from working backwards.
Good. So now what does working backwards look like in this circumstance? Working backwards looks like, where's my contradiction going to be? So you start with adding the assumption, and you look at the given premises, but there's no given premises. The first thing that stands out when I look at line 1 is that I've got A in there twice. So my first thought is, somehow A is going to, one half of the A is going to turn negative, the other is going to be positive. So that's what I'm going to look for. And then as soon as I use NIF, and I break out A and B, and I get, in step 3, I get that A turning into not A. I'm like, okay, now there's my not A. So where's my A going to be? And I yank it out of that statement 2. So that's kind of how working backwards looks like here. So it's where's the contradiction going to come from? And sometimes it's hard. Sometimes you want to work it forward and just ask, what are the steps up? What are the inferences I can do? Sometimes you want to just try to work backwards and say, well, where am I trying to end up? And here's what's going to make things really fun. Increasingly, we are going to get to problems where there are multiple correct ways to do things. So sometimes there'll be several right ways to do things. There's still going to be an infinite number of wrong ways to do things, but there might be 2, 4, 8 correct ways to do things. Sometimes some of those ways will be, involve an extra step or 2. But there's not going to be just one right way. Kind of like the lift. Yeah. Oh, absolutely. Yeah, that's no harm, no foul. That is completely trivial. So that's 110% okay. And it would also be okay if, and this is something I do a lot, instead of jumping right to statement 5, usually when I do something like the AND rule, I automatically infer both halves. So when I do this, often it would be a step longer, and there'd be a step between 4 and 5 where I just pull B out of statement 2 because I can. Because sometimes I don't know, maybe I'll need the B later. And it turns out, in this case, it was obvious that I wasn't going to do it. But sort of my method is to infer all the things that I can, because I want all the tools at my disposal that I might possibly need. But sometimes that ends up with me doing an extra step or 2. But in logic, that's okay. Yes, sir.
All right, so I'm a little confused how you're drawing out these different pieces of information and where you're going to come to the conclusion. So you're assuming the opposite of the original statement.
Right.
At first, but then you draw out A by B, but when it already be negated.
No. The rule for negated conditional is you always take the match, the affirmative version of what's on the left side of the arrow. So if the left side of the arrow does not have an extra negation, you don't have negation. The only one of the negation rules that gives you both sides negated is the OR. Negated arrow gives you the match of what's on the left and the opposite of what's on the right. So just like, so let's do this with something simpler. From negated arrow, from negated if A then B, you get out the match of the A and the opposite of the B. That's the way NIF rule works. So the thing that many people confuse it with is this rule, the rule for negated or. Negated or gets you not A and not B. But negated arrow gets you the exact match of what's on the left. That's the difference between or and if then. And that's why we need to have those S&I rules down cold, because we're going to need to use those in multiple steps. All right, let's do another one together. Let's prove from if A then B that if not B, then not A. All right, so we're given if A then B. Step one is to assume the opposite of the intended conclusion. So instead of if not B, then not A, we add an extra negation outside the parenthesis. So then we look at 1 and 2, and 1 and 2 are all we have to look at this point. At this point, I go systematically and I look for S rules to use. And then if there are no S rules to use, then I go to I rules. So there's no S rule to use with 1, but there is an S rule to use with 2. And as we just said, what the S rule for negated conditional does is you get the exact match of what appears on the left side of the arrow. The exact match is negated B. And we get the exact opposite of what's on the right side of the arrow. And on the right side of the arrow, we have not A. So we get the opposite of that, which is A. All right, so then we're at this point. We've got 1, 2, 3, and 4. We've already used statement 2. So at this point, I would look at statement 1 and say, can I do something with statement 1? And the answer is, yes, there is. Statement 1 says, if A, then B. So if I can plug in an A, I can get a B. So I take that A that I got in step 4, I plug that into if A, then B in step 1, and I get out B. But once I do that, I then have a direct logical contradiction, because 5 says B and 3 says not B. So we can't have B both true and false at the same time. So because of that, I can go back to statement 2, the assumption, and say this assumption I made must be incorrect. So in step 6, I say the proper conclusion is if not B, then not A. That's inferred from statement 2 because statement 5 and 3 contradict. Now note, this is one of the problems that there's a second correct way to do it. Does anyone see a second correct way that this problem might have been done? What could you do different and still end up with the exact same conclusion? This step right here, step 5, instead of combining 1 and 4, if A, then B and A, I could have combined 1 and 3. 1 says if A, then B. 3 says not B. From those two, in step 5, I could have gotten not A. And if I'd gotten not A, then 4 and 5 would have contradicted, and I still would have concluded the same way in statement 6, other than instead of 3 and 5 being not B, It would have been 4 and 5, A and not A, contradicting. So again, increasingly I'm giving you the tools to be grown-ups, sort of logically speaking, where there are more than one right way to do things, and you can do the one you prefer. All right. Now, let's do one over here together. From A, we want to prove the truth of A or B. What do I do first if I want to prove the truth of A or B from A? Yes. Good. So first thing I do is I'm going to block this off. I'm going to make a nested assumption. I'm going to assume either, actually, yes, I'm going to assume neither A nor B is true. And that is the assumption. It's the exact opposite of what I want to prove. So the goal is to take this, prove it leads to a direct contradiction, and then prove A or B. So that's where we're going with this. What can I do next?
You derive not A from A or B.
Good. So from step 2, I can derive not A, and I can also derive not B, because this is a negated OR. So from the NOR rule on statement 2, I will derive not A, and I will also derive not B. Although you only said not A because that's really all we need. Because what do we have at this point? What do I do next? What have we been trying to get? We have a direct contradiction. 3 says not A, but statement 1 said A. So 1 says A is true, 3 says A is false. And because of that, I can close off this indirect proof section, and I can conclude either A or B must be true. Why? It's from 2, because 1 and 3 contradict. And bam, we're done. Yes,
A quick question with exactly this data set.
assumption.
All right.
So what we're doing over here on the right is we are explaining where these different things come from. And that is a good practice for you to do because it helps you know what you think you're doing. And it's good for when you're trying to communicate your proof to somebody else. So when I'm grading these or looking these over, I can say, oh, they thought they were using this rule here, but they used it incorrectly, and that's why they did that. Or I can say, oh, how clever. It would have never occurred to me that you could have done that. But that was something that could be doing at this point. So yeah, over on the right, I'm just writing down an explanation for what rule, what tool I'm using. All right, let's do another one. Let's do if A, then B. If not A, then B. B. All right, what do we do first? Yes,
we assume not B.
good. So we always start by assuming the opposite of the intended conclusion. We want to block that off, keep that separate from our given statements. So we've got not B. What do we do next? Yes,
Just say if then we'll find that, not be there for not A.
good. So we can look at number one and we can say, well, from the empty error rule, it says if A, then B. But when you have the opposite of the right half, you can infer the opposite of the left half. And you can get not A from 1 and 3 MT right to left error rule. And surprise, surprise, you can do the almost exact thing on statement 2. Statement 2 says if not A, then B. You can reuse the not B, and you have the opposite of the right, so you'll get the opposite of the left. The opposite of not A is A. So from 2 and 3, MT error rule, we get A. And as soon as we've got that, we have our contradiction. So the moment we've got our contradiction, we then can go 6. We are trying to get the opposite of not B, so we get B from 3, because 4 and 5 contradict. And again, that's sometimes called RAA, or indirect proof. All right, how are we doing? We coming along? Those of us who were maybe wavering a little bit before, we coming along a little bit better? Good. All right, let's do a hard one. So you're saying, oh my God, those aren't the hard ones? All right. Here, I'm going to give 3 statements, A or B. If A, then C. If B, then D. And from that, we're going to prove C or D. All right, what do I do first? All right, I want to hear somebody else say it. I know you know the right answer. What do I do first? Yes. Good, assume the opposite of what I'm trying to prove. So I'm trying to prove either C or D. So my first thing to do will be to assume the opposite. It is not the case of C or D. And this is our assumption to be disproven. All right, what do I do next?
You can use the normals here. If, not C and not D.
Good. So I would look at 1, 2, and 3, and I can't do anything with 1, 2, and 3 because these both require, all 3 of these require I rules. And the I rules require a combination of these statements plus either matching or denying something. So I don't have I don't have anything I can do with those. But if I look at 4, I can get 5 and 6. With the NOR rule, I can get not C, and I can get not D. Now, this isn't part of the method, but one of the things I always like to do, I always like to put a little check mark next to the complex statements that I've used. Not because not because you absolutely have to use all of them, but usually you use all of them. So if I've already used one, I look at the ones I haven't used. All right, so what do I do next? Yes?
Well, not C should be able to get not A from 2.
Excellent.
And with not B should be able to get not B.
All right, well, one thing at a time. So we'll plug 5 into 2, and we'll get not A from 5 and 2 using the MT right to left arrow rule. And then I'm going to start a new column. And then I'll do what you suggested. So we've used 2. So then I'll also use 3. 3 says if B, then D. But 6 says not D. So we can get not B from 3 and 6 MT right to left arrow rule. All right, what should I do now? Well, here's what I do. I would look at this and say, well, look, I've used 2, 3, and 4. 5, 6, 7, and 8 are just simple one-letter statements. So the key to the next step is almost certainly going to be something in statement 1. So is there an inference I can do with statement 1? And the answer is yes. From 1 and 7, 1 says either A or B, but 7 says not A. So step 9 will be to infer B from 1 and 7, the DS or rule. And then look what we have. Then we close it off. We say step 10 is we've proven either C or D must be true. How? It's from statement 4 because 8 and 9 contradict. And we're done. All right, how are we doing? All right, give me 2 thumbs up if you've got it. All right, give me wavering if you don't have it or don't quite have it. All right, so we're getting there, not quite there. Questions? Where are we getting stuck? Those of us who aren't all the way there. What are we? How can we move you along a little bit?
I think it's mainly just trying to keep track of everything, making sure that everything goes where it's supposed to go.
Yeah, I mean, increasingly these get complicated, this is a 10-step proof over here, which is why it's important at this step we want to have those S and I rules down absolutely cold, and now we need to have the basics of the method down pretty cold. So the method is step 1, take the opposite of the intended thing you're supposed to prove, take that along with the original given statements, and start doing every S and I inference that you can, or work backwards towards what you're trying to get to. And the goal is to get to a contradiction. So look for a letter that there's more than one way to get a true or false version of it, and try to get that is both true and false at the same time. Some general tips. These are not hard and fast rules, but generally you use each of these compound statements at least once. So if there's one that I haven't used, I start staring at the one I haven't used and start trying to figure out what do I need to plug in to get there. And again, this is one where there was more than one right way to do this one. For this final step, instead of getting B, I could have gotten A from the combination of 1 and 8. And then instead of 10, the contradiction would have been between not 8 and 9, B and not B, but between 7 and 9, which would have been not A and A. We also could have done 7 and 8 in reverse order. So again, there starts to be multiple right ways to do things. I will leave a couple minutes at the beginning of next class. So if there's any more questions on proofs, please raise it then, because we're going to get into something even harder for next time, 7.2 on reputations. So I want to help you with 7.1 before we plow forward to the next thing. All right? All right. Keep on the perseverance. We have 9 days left. Hang in there. The end is nigh. Thank you.